Hi, my name is Koen Verhagen. This is a post-recording of a presentation that I made at the IoT workshop that coincided with the 2018 EOS ESD Symposium. We're addressing two questions. Is 1 kV enough for IoT ESD protection? And do current test methods and models apply? This presentation was originally targeted towards an audience of general IoT professionals, not specifically ESD engineers. First, I'd like to frame and give you some kind of a problem statement by stating why are these two questions asked. Next, we'll focus on the challenges in IoT semiconductor design, introduce our method for risk analysis, present to you 7 case studies that address those two questions, and finally conclude. So why these two questions? This is a bit of a personal experience story. Brief history of ESD demands. Going back to the year 2000, we see the typical requirements: 2 kV HBM, 200 volts MM, 1 kilovolt CDM. The qualification is basically defined by the weakest pin, and the whole process of qualifying parts is basically focused on the production and assembly life of an integrated circuit, basically being an unpowered packaged IC in a very controlled environment. We go 2008, and then we start seeing a lot of pin exceptions and non-standardized tests. For example, suddenly we see different CDM requirements for corner pins versus other pins, where corner pins are required to reach a higher level of CDM, or the other way around, actually the other pins can see a lower CDM performance. We also see people making trade-offs between the robustness of the chip and the speed abilities of the signal applied to the pins in high-speed and RF applications. We see different requirements, specifically much higher robustness requirements for pins that are having external connections, like in USB and HDMI. And also we're seeing people experimenting with applying human body model and machine model pulses on powered integrated circuits. Fast forward another 6 years, and we see a lot of diverging trends and what I would call creative testing. On the one hand, we see the lowering of historical levels, basically leading to the proposition that 1 kilovolt is enough. Basically avoiding that the weakest pin defines the specification. At the same time, we see an increase of specialty demands. We've seen anything from a requirement of 100 volt human body model performance all the way up to 24,000 volt HBM. At the same time, we do see that system and automotive and search requirements are added to an integrated circuit on the chip level. And we see a lot of creative testing and, in my opinion, a lot of overkill. We're seeing CDM testing on dies or on wafer level. We're seeing, maybe this is one of the most creative ones, the cut cable testing for interfaces. Just trying to explain what it is, but it's basically when for instance, a USB system needed to be tested, I've seen people using a USB cable that is cut, and basically a system stress is applied between signal lines or connections here that are in the cable that's normally never accessible by a user or in a system. We see system stress on devices. We see zap gun testing on powered ICs. We see all kinds of creative testing. I think also very important is, when we consider those two questions, is that there's basically two sides to the story or to the community. On the one hand, we have the ESD design community, and the job there is to mitigate the ESD hazards. And the important question there is, how can I make the mitigation of the ESD problem more or most cost effective? So how can I reduce my cost? How can I increase my efficiency, at the same time also my quality? The same question or the same considerations for cost and quality are definitely also asked by the people that are the customers of that community, basically the ones that develop the IoT systems themselves. And they see an omnipresence and use of their electronics, meaning new applications, new environments, new packaging. It's very good for their business. That's what drives their business. And their question is different. Their question is, will my product be reliable and robust enough? And so two communities are trying to answer our two questions, but we should keep in mind that they have a totally different perspective. Let's first have a look at the challenges for semiconductor design in IoT. Internet of Things. It's basically a billion things. According to a Cisco study, 20 billion devices by this year, 2020. Basically, stuff everywhere, everything connected to the internet. It's a network of physical devices. It obviously needs electronics. It's basically collecting and exchanging data. And with that, you basically have endless opportunities. So that's kind of the framework for IoT. What are the challenges? Well, obviously, we're talking about connectivity, mostly wireless connectivity. We need standards because all of these things need to talk to each other. There needs to be compatibility. There's a very important question about security and privacy. There's challenges about sensor integration and also in general, as always, cost reduction. But what we're going to focus on in this presentation is more the semiconductor stuff that we can address with as a designer is looking at high performance requirements, low power, the small form factor of the systems, the packaging, the robustness in general, and the reliability of the IoT devices. Before we dive into the specifics, let's present our risk analysis method. We borrowed the process, the system that is defined in the ISO 31000 specification. Basically, it's a very straightforward flow. You identify the threats, you assess the vulnerability, you determine what the likelihood is of something to happen, and you determine the impact when something happens, basically defining a risk matrix that is shown on the right-hand side, leading you to a risk assessment that could be none, trivial, low, below moderate, moderate, tolerable, substantial, major, to intolerable. Basically, it helps us to define the risks, and once the risk is defined, we can address how to mitigate it. In general, what are the threats in IoT or for IoT devices? Well, there's a few obvious ones. First of all, when we look at the use, IoT should be and is everywhere. It's in our daily lives. It's rather uncontrolled. The use locations can basically be anywhere and everywhere. It can be remote, it can be embedded, as the picture is showing you here, really anywhere, everywhere. The environments are unknown as well. They could be very harsh, and we will see more and more IoT applications where there is non-standard electrical overstress, where there is electromagnetic interference, where there's a lot of noise. So the threats are omnipresent. I think we can say that. What about vulnerability? Thinking about an IoT device. As we said before, we're talking about a data exchange, so a data connection, and in many cases, a high-speed data connections, which means for semiconductor designers, we're looking at designs with very sensitive gates, thin gate oxides. We're using antennas that are basically receivers for signals, including unwanted signals like overstress signals. And at the same time, we need to consider the signal integrity of our IoT device. We have typically some shielding material that are exposed. We have exposed connectors that can absorb or are basically there and can see a lot of overstress. We have a very small form factor. We have very short distances on board. We may have TVS devices, but in general, we have the omission of TVS devices, and also the packaging of an IoT device can be non-standard. We have direct die bonding, die connections, not classic package devices, but glued on dies, etc. How do we assess that vulnerability? What are the tools that we have? Well, we have our traditional ESD device level test methods, human body model and charge device model mainly, and also latch-up testing. There's another set of tools that we can use from the system level testing community. We have the IOC 61000-4-2 HBM stress, the 61000-4-5 surge testing, and also various methods for EMC. In addition, as I was alluding before, there's a bunch of custom setups for electrical overstress, powered IC testing, and also transient latch-up. What is the likelihood for ESD stress to IoT? Here we should again make a difference between what the exposure is prior to the development, the so-called the old days where we were focused on manufacturing IC assembly, also the system assembly, in this case IoT assembly. And we look at that world, basically I can already tell you, and everybody will agree, 1 kV and the traditional models are likely enough, provided of course good ESD control is in place and you have a controlled environment. However, when we look at ESD exposure during functional operations, as already alluded to as well, there are varying non-predefined environments, locations, and applications. And we don't really know what the exposure is in terms of frequency, in terms of stress level. So that's going to be our challenge in IoT design. What's the impact in a very general way? We can have soft errors and hardware errors, hard errors. Soft errors, sometimes a request, a reset is required, very simple. A hard failure, typically permanent physical defect, is another level of problem. But then again, when you look at the IoT applications, the impact of that is very much different. The result of a soft error can be ranging from something that is annoying to something that is lethal. If you're driving your car and your DAB literally skips a beat, okay, it's annoying that the music wasn't smooth, but okay, you'll drive, you'll live. However, if your ADAS system skips a beat, well, you might not live. So that's a whole different thing. Also, when a reset is necessary or a replacement is necessary, we should consider the use and the environment where the IoT device is implemented. If we think about in-body applications in a human, we don't want to just cut up people all the time just to replace an IoT device. It's totally not done. It cannot be done. Also, sometimes we have distributed networks of a very, very large amount of remote sensors. They're not easily accessible to replace. So, let's address and look at 7 actual IoT applications in the field and how we have come to conclusions and what kind of conclusions we have made with regard to the 2 questions that we're asking. Just to remind you, we are going to use this matrix of the ISO 31000 standard. We're basically going to look at the likelihood and the impact of an ESD stress to the IoT device and try to determine what the risk level is. From there, define a method, define a solution, define a mitigation way, and I will very briefly highlight those solutions. Case number 1, IoT at the cloud side. IoT connects billions of things. via the cloud. What's the cloud? The cloud is a bunch of data centers worldwide. In 2018, it was estimated there were about 8 million data centers, and every data center has multiple 10,000s of servers in each data center. And what we're looking at here is the server network connections. They are connected over short and long distances. They typically are high speed to very high speed. We can go up all the way to 100 gigabit per second. It also includes optical communication. So that's the case. We're looking at silicon photonics here, basically a silicon integrated circuit and a photonic IC integrated in one package. So it's complicated in that way. And so what's the risk assessment of this situation? Well, first of all, the threat. We are working in a very ESD controlled area. The vulnerability is the very high speed interface pins. So the likelihood something happens is rather low. And the impact is moderate. So according to the matrix, we have a low ESD risk. So what was the solution? Basically, the devices were tested according to the human body model. That's the ANSI ESD Association Standard Test Method 5.1. And the protection levels that were specified was for most of the IOs, we're using the old 2000 volts level of performance. However, for the high-speed IOs, because there's a very low capacitance requirement due to the speed required, was reduced to 200 volts, human body model. The details of the technical solution is that very thin gate oxide transistors were used, both in the 28 nanometer and 16 nanometer nodes, and a very low parasitic capacitance was achieved for the ESD protection level of 200 volt human body model on the high speed pins, in this case 56 gigabit per second. Case number 2, industrial indoor positioning. Basically, a project where ESD protection was needed for positioning sensors, basically RF tags. So it's industrial use. It happens in many locations. There is the 802-15.4a standard, 8.5 gigahertz wireless interface, and very specific here, the requirement of a 10-year lifetime of that tag from a 1-coin battery. What's the risk assessment? Well, the threat, we have the industrial environment and use. The vulnerability is we have a very small package and a very small form factor. The likelihood of something to happen is a little bit below moderate. The impact is moderate. The overall risk assessment is a below moderate ESD risk. Hence, the stress model that was selected here was again human body model and the protection level 2000 volts performance, including on the wireless IOs. We could have lowered that, but it was possible to do it in the target technology. In this particular case, 2 generations of products were made in 90 nanometer and then 40 nanometer. The parasitic capacitance specification was to be below 100 femtofarads, which could be achieved together with a very low leakage introduced by the ESD protection, in fact below 100 picoamps, guaranteeing a 10-year lifetime on a coin battery. Case number 3, NFC, near field communication. NFC is basically something that will simplify or does simplify our everyday tasks such as payment, transportation, networking, mobile marketing. What's the risk assessment of this situation, of this application? Well, the threat is we have a daily, everywhere use and environment. These devices are used everywhere in all kinds of situations. The vulnerability or the big concern is the signal integrity and on the antenna pin. What's the likelihood of something to happen? It's relatively high, just because of the threat and the vulnerability. The impact is not so bad. If your boarding pass doesn't scan, you can scan it again, or the friendly person behind the counter will certainly help you. The risk is moderate for ESD. So what was the conclusion on this project? We decided together with the customer to use the human body model test 2000 volts, and we also applied an EOS electrical overstress test for up to 10 volts. The custom solution included the use of and the protection of very sensitive thin gate oxide transistors in 55 nanometer technology, and it also included the use of a custom designed clipping circuit that basically both keeps in mind the signal integrity requirements and the ESD protection requirements. A good signal may not be viewed or interpreted as an ESD overstress, and therefore should be not clipped. However, a true ESD event should obviously be clipped. The clipping circuit that was designed and that accounts for both the antenna requirements and the ESD requirements. The output of that is shown here on the right hand side, basically reshaping the signal to avoid very high frequency distortions on the signal and to preserve as much information as possible. A fourth case we've worked on is body implanted devices. It's getting more interesting here. What we have is we have a wireless connection for signal and power. We have high voltage electrodes, and we need a very low power design for obvious reasons. The threat, well, we have a shielded embedded use, so it's not so high. However, the vulnerability definitely is here in the electrodes, the 18-volt electrodes. What's the likelihood of something to happen? It's on the second column B, and the impact is, it's going to be higher, because if something happens, this is a body implanted device, so we cannot just ignore that. This leads up to a moderate ESD risk. So what was selected in this particular case? Well, in the end, the human body model was used. However, it was an increased performance requirements of 6000 volts, not the standard 2000 or 1 kV, but 6 kV was applied. The specifics here is that the power, or the power consumption, had to be ultra low, and the leakage of the ESD clamp had to be very low. In this particular case, less than 10 picoamps at body temperature. There's no meaning here to look at 125 degrees C, because at 125 degrees C, well, the human does not survive. So you have another problem. 37 degrees C is a good target point for the leakage specification. Case number 5. We worked on some wearable devices. It's basically a wearable fitness tracker with a Bluetooth connection, wireless GPS, with a MEMS gyroscope, and obviously again a low power requirement. Not a coin battery, but you have a wearable device. You want it to have a certain lifetime. The threat is in the everyday use and environment. The vulnerability is the loss of signal or the signal integrity. The likelihood of something to happen is very high, because we have fast moving people in all kinds of environments. The impact is relatively low. The risk is judged as tolerable. So what was the end result? Basically, the human body model was selected, 2000 volts performance. The custom solution details are that, again, very sensitive thin gate oxide transistors were protected in 55 nanometer technology. The parasitic capacitance needed to be very low, but not extremely low, 150 femtofarads. And there was an overvoltage tolerant or 5-volt tolerant analog I/O requirement. Case number 6, smart home application. Basically, internet-enabled button or sensor. Wi-Fi connected, low power for obvious reasons, and a wide variety of functions are possible, hence also application environments. The threat, That's high because everyday use, environment not known and uncontrolled. Vulnerability is in a very small form factor, and the packaging and package integration. This leads to a substantial ESD risk because the likelihood is high and the impact is moderate. It depends on what kind of system that will get a runner's signal or operation. The conclusion was for this application that a system level stress needed to be applied. In this case, it was the IEC test 61000-4-2. Up to a level of 15,000 volts air discharge. The solution was integrated in a 0.18 micron technology. Very high TLP currents were required, so that's how the ESD design was specified, more than 20 amps of capability. In this particular case, we used an SCR-based design, silicon-controlled rectifier, because we needed to have something that is viable in terms of on-chip area use. And an SCR, if built properly, can be the most area efficient, effective ESD protection. In addition, we had very short connections on board. Case number 7, this is the last case, is from the industry 4.0, sensors in factories. Basically used for predictive maintenance, constant monitoring of temperature, pressure, frequency. There's an embedded video that I'm just going to let you play here while I continue my risk assessment. The video basically shows the application in the field actually using the Sofics solution. The threat is high because we have a very noisy industrial environment. The vulnerability is that basically you have a very small form factor, and also the packaging is it's as you can see, a glue-on device. The likelihood of something to happen is high. The impact in this particular case is also relatively high, so we now have a major ESD risk. What was used in this particular case is again the IEC stress model, again 15,000 volts air discharge, and in addition here again is the ultra low power design. In this particular case, the target specification was to stay below 20 nanoamps. In this particular case, the requirement was to have a 20-year lifetime on a single coin battery. So we are at the end and need to come to our conclusions and answer those two questions. Is 1 kV enough for IoT ESD protection? And is 1 kV enough? Well, I would say in pre-development or pre-deployment, yes. After deployment, we have a different story. The risk really depends on the application and the process. The additional trade-offs need to be made will add complexity. And in general, I think the 7 cases that I have presented have indicated or illustrated that it's not always possible to apply a one-spec-fits-all ESD stress requirement. Do current test methods and models apply? I think I have demonstrated with the case stories that for IoT, frequently additional reliability and custom test methods are required. While often human body model is used, when it comes to very high risk applications, we typically see and apply IEC test methods. And for very specific applications, we will define and add additional electrical overstress tests. In general, as a piece of advice, I would say please consider to include the EOS and ESD considerations very early on in your design phase so you can identify the solutions for those new threats. With that, I hope I have answered the questions that were posed and that were the main topic of this presentation. Thank you very much for listening. You can find more about Sofics on our website. You can also find our regional contacts there. In addition, you can always contact my colleague Bart Kappens or myself, Koen Verhagen, the presenter of this presentation. If you're in for more movies, there are 3 40-second videos on Sofics that you can assess through these QR codes. Thank you very much for your attention and have a very nice day.